Good day, everyone. My name is Ilya, and I want to present to you a work on team called Classifier for Cardiovascular Disease Prediction based on Boosting Models and XAI by Olesya Machurat, Ilya Bulikonich, and Yuliana Machurat. The aim of this study is to develop and evaluate an optimized ensemble classifier for cardiovascular disease prediction that balances high predictive accuracy with clinical interpretability using explainable AI, which is SHAP. The objective is to deliver reliable detection with high recall while maintaining strong overall performance. Explainability is treated as a first-class requirement. Each prediction is accompanied by global and local SHAP explanations, allowing clinicals to see which variables increased or decreased the predicted risk. The problem setting is binary classification. Given a patient's clinical features, decide disease or healthy, data are split into training, validation, and test subsets to prevent leakage. Resampling is performed only inside training faults. Key challenges include class imbalance, which is healthy patients substantially outnumber patients with cardiovascular disease. Feature heterogeneity requires specialized encoding and scaling, and interpretability. Clinicians must understand why the system makes a particular decision. The pipeline begins with preprocessing. Numerical features are normalized to comparable scales. Categorical features are encoded with robust schemes, one hot or ordinal. These steps reduce spurious variance and make downstream learning more stable across models. To address class imbalance, smooth ENN is applied. Minority oversampling smooth followed by cleaning of noisy majority samples ENN. This hybrid strategy preserves informative structure while reducing overfitting risk typical of plain oversampling and undersampling. Base learners include logistic regression, random forest, XGBoost, and LightGBM. Each base model is individually tuned, biasing iterative search with a recall-oriented objective. The final decision uses soft voting probability averaging with a configurable threshold, allowing operating point adjustments for different clinical departments. Explainability is integrated after training. For tree-based models, tree SHAP is used. For logistical regression, analytic contributions or linear explainer. For the ensemble, contributions are aggregated consistently on a probability scale. Explanations are computed only on non-resampled validation faults or on an external holdout to avoid leakage. Few words about comparative analysis. Relative to prior lines of work, Smooth plus XGBoost pipelines are simple and strong on tabular data but can inject noise and lack native interpretability. Hybrid pipelines adapt across datasets but are harder to reproduce and more dataset dependent. Stacking ensembles may generalize but complexity and reduced transparency due to the meta model. In the present approach, a soft voting ensemble with per model optimization and SHAP explanation is adopted. Strengths are high recall, stable fault-to-fault performance, transparent global and local explanations, and a strict no-leakage protocol. And the limitations are high runtime and memory than a single model, somewhat more complex deployment, and the need for external validation. The trade-off is a modest computational overhead in exchange for better sensitivity and interpretability suitable for screening. A public heart disease dataset was chosen, merging well-known sources including Cleveland Hungarian StatLog. After cleaning and harmonization, there are 1,025 patients, which is with 13 inputs features plus a binary target. Examples: age, serum cholesterol, resting blood pressure, maximum heart rate, chest pain type, resting ECG, thallium test result, and number of major vessels. Evaluation relies on standard metrics derived from the confusion matrix, accuracy, recall, precision, F1 score, and AUC ROC. In clinical terms, true positives and true negatives are correct identifications. False positives are healthy patients flagged as diseased. False negatives are diseased patients missed by the model. Giving the clinical cost, recall is emphasized. Confusion matrix on the test set, the ensemble produced true negatives 87, false positives 13, true positives 93, and false negatives 12. These profiles indicate strong sensitivity, low false negatives with an acceptable rate of false alarms. The counts reflects on a screening-friendly balance where missing true disease is minimized. And ROC curve lies clearly above the diagonal with AUC 0949 indicating solid separability across thresholds. Threshold tuning can be adapted to context, more sensitivity for early screening or more specificity for confirmatory scenarios without retraining the models. About the performance, when single models are compared with the ensemble, the soft voting approach provides the best overall balance across accuracy, recall, F1 score, and AUC ROC. Boosting models XGBoost and LightGBM are individually strong, but ensemble demonstrates greater stability and sustains high recall without a major precision penalty. Global SHAP analysis ranks clinically meaningful contributors at the top. Chest pain, a number of major vessels, and thallium test show the strongest positive impact on predicted risk. Age and sex are consistently important. Exercise-induced angina and ST depression tend to increase risk at higher values, while maximum heart rate often acts as a protective factor. These effects align with domain knowledge and support trust. At the patient level, local SHAP explanations show exactly why a case was judged high or low risk. For high risk profiles, risk-raising signals commonly includes pathological thallium categories, multiple affected vessels, ischemic chest pain, and marked ST depression. Higher maximum heart rate may lower the predicted risk. Such narratives make decision auditable and clinically interpretable. Efficiency. Runtime and memory were analyzed for deployment planning. The ensemble requires roughly 6 seconds and has a memory footprint around 8 megabytes, larger among the tested models. XGBoost, LightGBM typically run in more or equally to 2 seconds with strong accuracy, and logistic regression is the fastest with lower predictive performance. These values characterize the trade-off between maximum detection and stability and resource usage. The results validate that combining tuned heterogeneous learners with balanced training improves cardiovascular disease prediction while remaining explainable. SHAP demonstrates that the model relies on clinically meaningful variables supporting trust and adoption in decision support. The ensemble's high recall aligns with the screening priorities, minimize missed disease while still maintaining strong AUC. And about limitation and future work. External validation on independent cohorts is still required to confirm generalization. Resampling methods such as SMOLT and SMOLT ENN may overfit on very small datasets if misused. The leakage-free protocol mitigates the risk. The next steps are integrate into clinical decision support, plan prospective testing, adapt the pipeline to additional datasets. In conclusion, hybrid soft voting ensemble with class balancing and per model optimization delivers a strong balance of accuracy, recall, F1, RUC, AUC. Recall-oriented optimization is appropriate for medical screening, reducing false negatives. SHAP provides interpretable global and local explanations. Key risk factors align with domain knowledge. The approach combines predictive performance with interpretability, supporting clinical applicability. Thanks for the attention.